Wow, just look at this thing. It's sleek, it's balanced, and honestly, it's kind of remarkably human looking. This is Tesla's Optimus Gen 2, standing ready. But what you're looking at isn't just a metal shell, it's an absolute masterclass in biomechanical engineering colliding with artificial intelligence. Welcome to this explainer. Today, we're going to look way past the glossy exterior and unpack the exact physical and digital anatomy that makes this one of the most advanced humanoid robots in development today.
The anatomy of a humanoid inside Tesla's Optimus. We're going to break down exactly how you take the brain of a self-driving car, build it a custom-engineered body, and teach it to actually operate in our world. Here's our roadmap for today. The Gen 2 transformation, muscles of the machine, powering the humanoid, the FSD brain, and finally, digital dreams and simulation. Okay, let's jump right in. Section 1. The Gen 2 transformation. Shedding weight, gaining speed.
You really got to look at the sheer scale of the engineering optimization here. I mean, look at that weight drop, going from 73 kilograms down to just 57. That is a massive 16-kilogram reduction. And because it's so much lighter, and because Tesla actually swapped out those off-the-shelf third-party parts for their own custom actuators, the walking speed literally jumped by 30%. It's hitting up to 8 kilometers per hour now. It really shows you how custom, bespoke engineering completely transforms locomotion.
Now, this part is super interesting. It highlights what it actually takes to build one of these machines right now. So Morgan Stanley estimates the current bill of materials for Gen 2 is sitting somewhere around $50,000 to $60,000, which, might sound pretty steep at first, but remember, Tesla's ultimate stated goal for mass market production is to get this under $20,000. They are taking the exact same mass manufacturing playbook they use for their cars and applying it straight to robotics. If we break that cost down a bit further, you can see where the money is actually going. The legs take up nearly 40% of the cost. I mean, it makes sense for a bipedal machine, right? But check this out. Notice how incredibly expensive the hands and the waist are. Over 31% combined. This really just hits the nail on the head regarding the immense mechanical complexity you need to achieve human-like dexterity and balance. Turns out, building hands is really, really hard. All right, moving on to Section 2, muscles of the machine, the actuation shift.
To pull this off, Tesla uses what's called a frameless torque motor. As you can see by the definition here, these are highly, highly specialized. They completely strip away the shaft, the bearings, the end caps. Basically, you're just left with the stator and the rotor. So why does that matter? Well, the crucial point is that by ditching all those bulky traditional components, Tesla can embed these motors directly into the robot's joints. That completely eliminates the need for heavy reduction gears.
And because they're frameless, they have this hollow center. That hollow design is an absolute game changer. You can actually route the cables internally right through the joint itself, which saves massive amounts of space. In total, Optimus uses 28 of these custom actuators, that's 14 linear and 14 rotary, to make up its core musculature. It provides immense torque, but in a super compact package.
But what about delicate movements? Like in those crazy expensive hands we were just talking about? Frameless motors are way too big for that. So for the hands, they use coreless motors. You can kind of think of these as the fine motor tendons in your fingers. They use a totally ironless, hollow cup rotor design.
By getting rid of that iron core, you eliminate iron losses and something called cogging. That's that weird, jerky feeling you sometimes get with electric motors. Instead, you get incredibly smooth operation and just unmatched dynamic response. This specific ironless design is exactly what provides the high-speed response needed to give the new Gen 3 hands their 22 degrees of freedom. With 50 of these tiny actuators packed across both hands, Optimus can firmly grip a heavy tool or, amazingly, hold a delicate egg without crushing it.
Next up, Section 3, powering the humanoid, the stamina inside.
2.3, specifically 2.3 kilowatt hours. That is the exact capacity of the battery pack that is sitting perfectly balanced right in the center of the robot's torso, which actually acts as its center of gravity.
So what does 2.3 kilowatt hours actually get you in the real world? It translates to a full work shift. We're talking 8+ hours of non-stop light to medium factory operation. And here's a really fascinating little detail. It uses Tesla's very own 4680 battery cells. Literally the exact same battery cells that Optimus units are currently sorting on the factory floors in Texas right now. Plus, remember that 16-kilogram weight reduction we talked about earlier? That directly boosts its everyday stamina, meaning the robot actually needs less energy for every single step it takes.
Okay, let's get into the digital side. Section 4, the FSD brain, inheriting a mind.
We're honestly looking at a massive paradigm shift in robotics here. Traditional robotics heavily relies on explicit programming. That means engineers are sitting there writing hundreds of thousands of lines of C++ code, literally telling the robot exactly how to move its joints for every single possible scenario. Tesla? They threw all of that out. Instead, they use a single end-to-end neural network. They just feed raw camera input directly into this network, and it instantly outputs motor commands. The robot is essentially learning by observing, rather than being explicitly told what to do.
And how does it actually know how to interpret what those cameras are seeing? 8.2 billion. That is 8.2 billion miles of real-world vehicle data. You see, Optimus isn't starting from scratch here. It shares the exact same AI architecture as Tesla's full self-driving cars. It completely inherits the spatial reasoning, depth estimation, and object recognition of millions of cars already navigating the real world. In this framework, a robot is really just a self-driving car with legs instead of wheels. But how does a robot learn specific tasks, like folding laundry, without millions of robots already doing it? That brings us to Section 5, Digital Dreams and Simulation, the data flywheel. To teach Optimus totally new physical tasks, Tesla built what they call a neural world simulator. Now, hold on. This isn't your standard video game physics engine where some engineer had to manually code in gravity and friction. It is a learned simulation. The whole thing is generated entirely from real-world video data. And because it's trained on actual video, it inherently understands real-world physics. This practically erases that massive gap that usually exists between training an AI in a virtual world and having it actually operate in the messy real world. This is the absolute core of their synthetic data approach. They actually call them digital dreams. Basically, they take one single video of a human demonstrating a task, and then, using video generation AI, they hallucinate 10,000 variations of that exact same task. They change the lighting, swap out shirt colors, alter the approach angles. The robot gets to practice in these generated digital dreams thousands of times without ever moving a single physical motor. Let's walk through exactly how this training loop works. Step 1. Humans wearing camera rigs demonstrate the task. Step 2. The AI dreams up tens of thousands of those synthetic variations we just talked about. Step 3. Tesla's massive Cortex supercomputer, which is packed with over 67,000 GPUs, crunches all that data in just tens of thousands of hours. And finally, Step 4, an over-the-air update is sent out. The robot goes to sleep and wakes up the next morning fundamentally smarter, knowing how to do a completely new task. It's wild. Why this matters, and what you really need to take away from this explainer today, is the flywheel effect. Because of this shared architecture, every single hour an Optimus works in the factory and every single mile a Tesla drives on the road, the entire global fleet of cars and robots gets smarter simultaneously. It is an unstoppable, compounding rate of improvement, all fueled by literally the largest real-world AI dataset in existence.
Which leaves us with this final thought. We've seen the custom frameless motors, the 2.3 kilowatt-hour stamina, and these wild digital dreams generated by massive supercomputers. With Optimus already working in factories today and a long-term target price of under $20,000, how soon will this blend of bespoke hardware and neural network intelligence cross the threshold from the factory floor directly into your daily life? Thanks for joining me on this explainer. I'll see you next time.